So what we have in our example here is we have some scaffolding that is going to be used by a window washer. So this guy is going to get his squeegee out. He's going to wash windows, and you can see the windows. You can just barely see the windows. Now let's put some numbers to this. Our window washer is going to be an 80 kilogram window washer. And he's going to be standing at a point that is 2 meters from the left end of the scaffolding. And here I'm considering the left rope, I should say. And he's going to be standing at a point that is 1 meter away from the right end. Okay. Everybody with me on the scenario? Now I'm going to ask a simple question. What is the torque that the window washer exerts on the scaffolding about point O and about point P. Now I want you to observe the language that's used in this question. First of all, we're saying that the window washer is exerting that torque. Well, what force are we really talking about? We're talking about the force of gravity, aka his weight. Exactly. So we're going to need to first compute his weight, and his weight is, of course, what is his weight?
So 80 times 10.
Which is going to be basically 800 newtons, right? So that is his weight. Okay. So that's the first component that we need. We need a force. Second of all, we need a distance. And if we are considering point O, then the distance that we're talking about is clearly 2 meters. So we have a force with a distance. And the third thing that we need is the angle between, so that we can compute the sine of the angle between. And what is the angle between the force and the distance here? It's a 90-degree angle because gravity always pulls straight down, and the scaffolding is necessarily going to be horizontal, otherwise he's in trouble. So that when I now plug in, I can say that the torque exerted about point O, notice how I notate it, the torque exerted about point O is going to be equal to force times distance times the sine of the angle between. Notice that I'm not multiplying by the angle between, I'm multiplying by the sine of the angle between. What is the sine of 90 degrees? 1, yes. So that in this particular case, my term becomes invisible, and I get 1,600 Newton meters worth of torque. Great question. Are Newton meters in terms of torque the same as joules? Interestingly, weirdly, they're not. And you can think of them really as joules per radian.
But a normal Newton meter is a joule, right?
If I do force times distance parallel, I get joules, which gives me a change in kinetic energy. The torque is only going to be the tendency to rotate or that which causes angular acceleration.
Okay.
Until the object actually moves, no work is done.
Right.
So we'll come back to that later. But you basically have to multiply by a radian angle to get the work done. Okay?
That's true.
Yes?
Is there like any way in the units sense to distinguish between Newton meters as in joules and Newton meters as in torque?
Not really. You could technically write the torque as Newton meters per radian or joules per radian, but nobody really does that. It's just Newton meters. Yes.
Does sine 90 degree, does that go with the 2 meter, or does that go with the orientation?
It doesn't have. So think associative laws of multiplication. July.
So that, is that just a point at which the torque, what is that represent?
The O right here? Yes, that represents the point of rotation that we're talking about.
Okay.
So we're about to come back and do torque about point P. But we need to do one more thing before we move on, and that is consider orientation. Now this is going to be a little bit challenging, but we're up for it. The orientation is going to be either clockwise or counterclockwise, just like we had for our angles. And we're going to take counterclockwise to be the default positive orientation, okay? Now, how do you determine the orientation of a torque? What you have to do is to visualize the force and the distance right here. You have to visualize which direction of rotation this force would cause. Would this cause a clockwise rotation, or would this force cause a counterclockwise rotation? It's pretty obvious it's going to cause a clockwise rotation. And so because our default orientation positive is counterclockwise, we're actually going to call this negative 1,600 Newton meters worth of torque. And the negative sign indicates that it's causing a clockwise, has a tendency to cause a clockwise rotation.
Okay, so if it's clockwise, it's negative, counterclockwise.
Positive, exactly. Now you guys are going to have to be very careful with these positive and negative signs because you're going to want to look at direction up and down or left and right because we've been doing that for forces. That's not what you want to look at. You want to look at instead, does this cause a clockwise or counterclockwise rotation? So let's come back and answer the second question. What is the torque about P? Well, the weight of our man has not changed, unless he's been eating lots of snacks between when we solved the first problem now. So he is the weight is still 800 newtons. But now, when I draw that distance, here comes my 800 Newton force. About P, my distance is 1 meter in this direction. Here's my point P. And my angle is still a 90-degree angle. Notice that I'm pushing perpendicular, so my distance perpendicular is my distance in this case. That corresponds to the theta being a 90-degree angle.
Where's point P supposed to be located?
What's that?
Where's point P supposed to be?
Point P is located right here.
Oh, okay.
So that the torque exerted about point P, and there's my subscript again, telling me the axis of rotation. That's not an optional decorator, it's necessary. Is going to be 800 newtons times 1 meter, again times the sine of 90 degrees, which is 1. What about the orientation? The orientation now is causing this guy to rotate like this. That's going to be positive orientation, counterclockwise. So I'm going to put a plus sign on that. And what I get is positive 800 Newton meters. So notice again, as I said before, the same downward pointing force caused a negative torque about O, but a positive torque about P. Why? Because, well, basically, we were talking about pivot points that were on two different sides. Rotational points that were on two different sides. Sure.
And then there isn't like a sum of torque, like,
There's going to be
there's,
that. But it has to be about a particular point. So there's no meaning to summing up the torque here.
a few different points.
Doesn't do anything. All right, let's take a look at an example from a problem from your book. Let's take a look at number 24. Number 24 has an interesting feature, and that is that it has a sneaky angle. What happens in number 24 is that we have, oh, that's fine. We have two different wheels, one attached to the other. And we have three different forces acting on those wheels. One of them is a 35 Newton force. One of them is a 28 Newton force. One of them is an 18 Newton force. And they give the radii of these wheels as 28 centimeters for the large one, and 12 centimeters for the small one. And then they give this interesting angle, 135 degrees right here. And they now ask the question, what is the net torque about the axle? And the axle is the center right there. Okay? So there are several features about this problem that we're going to want to pay close attention to, but it's actually a really simple problem once you've paid attention to those features. The first thing is to identify that I have 1, 2, 3 forces, so that the net torque is going to be the sum of all 3 torques exerted by all 3 forces. That's the first thing to observe. The net torque is going to be the sum of all 3 torques exerted by all 3 forces. Okay. So I'm going to march through, and for each force, I'm going to compute force times distance times sine of angle between. And I'm going to write it like this. If I label this point as A for axle, then the net torque about the axle is going to be 35 newtons times its distance. Now here's the second place that I need to pay attention. They don't tell me the distance from the point of application of this force to the axle, but I can figure it out. It's the radius of the circle. That's exactly right. It's 12 centimeters. The 28 centimeters is the radius of the large wheel. See how it extends from A down to the, and the 12 centimeters is the radius of the small wheel. All right, but now I need the sine of the angle between.
Sine phi.
That's the tricky part. Because this angle mentioned here is 135 degrees, it's tempting to go, oh, that's my angle. Oh, put it right in there. But the angle in the sine of theta is not the first angle you see on the page. It is the angle between the distance and the force. The distance is the radius, and the force right here is tangent to the circle. What do you know from geometry about tangents and radii?
Is it going to be the same? 90.
It's going to be 90 degrees. A tangent is always perpendicular to the radius at the point of application. So even though there's a 135 degree angle in there, it doesn't matter. What really matters is that my tangent is perpendicular to the radius.
Maybe for the university.
Yep, pretty much. We are not going to use this 135 degrees in the problem at all.
Oh.
Yep. Finally, the thing we have to pay attention to that students are going to want to forget is the orientation. Is this 35 Newton force causing a clockwise or counterclockwise rotation? Clockwise. Therefore, minus. Now, we walk through the same process for the 28 Newton force. The 28 Newton force is at a distance of 28 centimeters from the point of rotation, and it is also tangent to the circle and therefore perpendicular to the radius. And it is causing a counterclockwise torque, like so.
So if the forces are tangent, that just means that the angle is 90.
Yeah.
Okay.
What was the justification for the 90 degrees?
Because a tangent is always perpendicular to the radius.
And
at the
the
point of
promise-
distance.
the
What's that?
promise stated it was tangent to the circle.
If you look at it, there's no way to read that other than it is tangent to the circle. And then finally, the 18 Newton force is also multiplied by 28 centimeters, and it is also tangent to the circle, but now it is pulling clockwise, so that we count that as a negative torque. Why is it pulling clockwise? Just imagine this
I see.
force in isolation. Imagine it pulls.
Okay.
What does it do?
Mhm.
Yep.
This is recorded, right?
Yep. Now, if we add all this up, what do we get?
You have to multiply out first.
Yeah, we have to multiply it out. Does it come out to be 0? I'm thinking not. Negative 44? Negative 140. We'll take that as read.
So could this
And it's,
zero?
Yep. So the net torque about point A then is negative 140 Newton centimeters, indicating that there's going to be a tendency for this thing to rotate clockwise under the influence of these three forces. Now I want to come back and observe how we visualize this correctly. Please notice that I did not use the angles of the forces relative to due east. See, this force is at an angle of 45 degrees relative to due east, and this one's at a 90-degree angle relative to due east, and that one's 180. None of that matters. The only thing that matters is the angle between the force and the distance at the point of application. And if those two vectors happen to be perpendicular, then your sine of your angle is going to be 1, and that factor will be invisible. Does that make sense? The only angle that matters when computing torque is the angle between the force and the distance. And if that angle happens to be 90 degrees, then there's
This would be the radius.
Now here's a question that sometimes comes up and troubles people. Sometimes you get like a fishing rod problem, where a guy's holding onto a fishing rod, right? And the fishing rod's like 2 meters, and all of a sudden the fish grabs a hold of it and starts pulling with a force of like 100 newtons or something like that. Big fish. And so this angle is now given as, let's say it's a 45-degree angle, something like that. And so the question now is, what is the torque exerted by the fish about point O? Okay. So we say that the torque exerted about point O is equal to 2 meters times 100 newtons, force times distance, times the sine of the angle between. And the questions people sometimes have is, do I use the 45-degree angle here? Or do I use the 135-degree angle that's caused by that? Good news, it doesn't matter. And the reason it doesn't matter is, looking at your unit circle, if you pick any angle, and the angle supplementary to it, the sines of those two angles are the same. So whether I choose the 45 degrees or the 135 degrees, I'll get the same value for sine theta. So if you have an ambiguous situation where you're not sure which angle between force and distance to use, if they're supplementary, don't worry about it. Does that make sense? Amy, you had a homework question. What was it?
19.
Number 19.
Yeah, Trinity.
Okay. A cooling fan is turned off while it is running at 800 revolutions per minute. How did you label that information? A cooling fan is turned off when it is running at 800 revolutions per minute. How did you label that information?
I did for, for the initial omega, I had 850 revolutions per minute.
Yes, exactly.
And then for the final omega, I had 0 revolutions per minute.
Good. And
And then for theta, I had 1500.
excellent. Very good. All right. So now it asks for the fan's angular acceleration. What symbol are we talking about here? Alpha. Okay. And what equation do you know that relates these four quantities together?
I did, omega squared equals omega initial squared plus 2 alpha.
Perfect. When you plug in all those numbers and solve, the first thing that I observe here is that I'm going to end up with a negative value. That's the first thing that I observe. And that gives me alpha equals negative 241. But what kind of units? They're weird units. They are revolutions per minute squared. And so when I go and check in the back, there are pretty good odds that they are going to have expressed their alpha in radians per second squared. Let's see if they did or not. Sometimes they do, sometimes they don't. Number 19, yep, negative 0.42 radians per second squared. And so your first thought when you look at this is, oh, I messed up. Well, maybe not. Maybe we just need to convert our answer to the appropriate units. So let's try that. That's 2 pi radians for every revolution. So there's that. Now, on the minute squared, be careful, because there's a minute for every 60 seconds. So there is a minute squared for every 3,600 seconds squared. Yep. And so when we actually do the computation, we get 241 times 2 pi which gives me negative 0.42 radians per second squared. Exactly as advertised. Now, in the second question, they ask, how long did it take the fan to come to a complete stop? And for this, I can use any of the pieces of information that we have here, but I like to use the given information if possible. So I can say that delta theta is equal to omega plus omega 0 over 2 times time, or 1,500 revolutions equals, what was it, 850? But now my time is in what units? In minutes. And so if I am comparing to the back of the book, and the book gives me answers in seconds, well, I know what to do. Does that make sense? Yep. So the missing thing there was the proper conversion of the squared units. Yeah,
And can we use a different equation?
yeah, sure. Yeah, because you have 4 out of 5 possible pieces of information, any equation that has time in it will be useful. The one that has t squared, probably not recommended. But certainly doable. I mean, you got the same answer, right? So that gives you some confidence. Let's see what we have. Well, we did 21 yesterday in class. Yeah. Mhm. Okay, let's call it a day.